Hi there. This lecture is about temporal errors, which are another kind of error, unlike the spatial errors we've seen before. So a spatial error results in the possibility for an attacker to access data outside the allocated space for a buffer. So this means that we can, for example, have an offset from the existing buffer. So temporal errors, the offset is not in the space dimension, but in the time dimension. So we have a buffer that will be suitable for usage in the future or in the past. But we do access it within the space bounds. We just access it at some point in time where it's not ready or not ready anymore to be accessed. So these are interesting cases because they are much harder to find than spatial errors, which means they are also relatively getting more common as we're doing more and more about the spatial errors. So this also means, of course, they're harder to exploit. So the main types that we will discuss here are use after free and uninitialized variables, where use after free means basically that we use the buffer after its intended usage was ended, so after it's been deallocated, and uninitialized variables are used before they were intended to be used, in particular before they were initialized with a value that can be read from them. Both are important classes of errors that remain even as spatial errors are being cleaned up. We start with the use after free vulnerability. So sometimes a program retains a pointer to a freed memory location. So it calls the free function on a malloc buffer, for example, or it retains a pointer to a local variable or an alloc buffer after a function returns. Now this pointer doesn't change, even though the memory was deallocated. It remains pointing to the same memory, but that same memory now gets another purpose. In first instance, it will be freed, but later on, it might actually be used for a future allocation, or in case of the stack, for a future stack frame. So the memory will be reused, but we have a pointer pointing to this block of memory, thinking that it's actually something else. Now this pointer is a dangling pointer. And when the program uses the dangling pointer to access memory, this is obviously a bug, because it's no longer pointed to the intended buffer. So the theory is that dereferencing a dangling pointer results in undefined behavior. This is what you'll find in a language specification. Now undefined sounds like we have no idea what's going to happen, but obviously that's not true. In practice, use after free vulnerabilities are actually reasonably predictable. Moreover, it is very likely that they behave normally in most circumstances. In fact, if in normal circumstances they behaved unexpectedly, you would expect them to be found in testing. So the remaining use after free vulnerabilities in a production program are likely those that do not expose any weird behavior in normal circumstances. Just as a buffer overflow has no impact until you actually put in more data than expected. However, typically, memory reusage patterns and memory access are predictable. So memory reuse depends on the way that the program allocates and deallocates memory, as well as the library that implements malloc. Access is also predictable because it depends on the program itself. And in fact, often it's possible for an attacker to influence access patterns by sending data that causes the program to allocate or deallocate memory of particular sizes. Now this technique is known as heap massaging, and it's often useful for use after free attacks. So what we essentially want to achieve is we want to create a dangling pointer, we want the memory to be reused, and then we can access this memory through the dangling pointer. Now, heap massaging can help us achieve this goal as an attack. Now let's go through the steps of a typical attack against the use after free vulnerability. So, we assume that the attacker is able to craft some input to override memory with attacker provided data. How does the attacker actually achieve this? First step, the program allocates the buffer to be used as a target. We call the buffer X. The program uses X to store some data. So far so good, nothing wrong yet. Program frees X. Now what happens now is that although X has been freed, there may still be pointers remaining to x. And these pointers assume that they actually point to x even if it no longer exists. So, now it gets interesting. The program allocates some buffer or variable y, which happens to overlap with x. Now, typically this would be a coincidence, because the programmer doesn't really know or care about the particular allocation patterns of the malloc library. But the deliberate attacker might very well predict what the malloc library is going to do, and make sure that memory allocations are timed in such a way that this allocation of y will be made overlapping, even though normally it would not necessarily be. Keep in mind this is important because it shows again it's very likely that the use after free vulnerability had no impact, while the programmer did nothing when an attacker did nothing with it specifically, but might have impact when a deliberate attacker tries to manipulate the memory allocator. So the next step, and this is where it goes wrong, this is where we get actual corruption. Now any data written to y also overrides some relevant part of x. And finally, the program then uses x, causing an incorrect result. So if the attacker wrote some data there that was particularly harmful inside x, even if it was permissible within y, then this would typically cause the program to behave exactly as the attacker intended. And then the use after free vulnerability is successfully exploited. Another thing here is that steps 5 and 6 can be swapped. So we could use the dangling pointer to corrupt some real data, or we could use the real data to corrupt whatever the dangling pointer is pointed to. Right? So in both cases, the situation might be exploitable, because we can unexpectedly for the programmer override some data with other data. Now that we've seen the high-level attack plan, let's see what the gory details look like with an example program. So here we see a program that first allocates a buffer x, writes something to it, frees the buffer, and then allocates the buffer y. So where is the bug? Well, the bug is in the fact that x is still used after it has been freed. So this is where something went wrong, clearly. Let's see. What is going to happen when we run this program? Well, first of all, we have the variable x, which is now initialized to point to the malloc buffer. Here the dark colored fields have been initialized and the lighter fields have not yet been initialized. Well, now we have a string copy, where we copy a fixed value to the buffer x. So the security of the program might depend on this value actually being there. This could, for example, be a validated path to something. Now, keep in mind, we're writing here with an offset of 8, which might seem weird, but this is because, if you remember correctly, there will be some corruption in the buffer whenever the buffer is freed in the memory allocator. So this +8 ensures that data is not corrupted. Of course, if the vulnerability is not deliberate, we don't necessarily expect something like that. But in many cases, even with some minor corruption at the start, the program won't notice until the attacker deliberately triggers it. So, now that we've performed the string copy, the value hello world is correctly written into the buffer. We free the buffer, and what actually happens is that this memory is marked as freed in the heap management system. However, nothing actually changes. The data is still there, and X still points to this data. So, except for the metadata of the heap management library, everything is still the same. Now, next, we allocate Y. So Y allocates some memory for another buffer, and this size of the buffer is tweaked towards the size of the parameter specified by the attacker. Now, why is this relevant, you might ask? It is relevant because in this case, if the attacker wants to specifies the right amount of data, the buffer will be reused. However, if the attacker specifies a much larger buffer, it's not possible to reuse the old memory chunk of 32 bytes. So this is basically the simplest form of heap massaging. We must allocate the right buffer size. Otherwise, we will not reuse the memory and the attack will not be successful. So now we have X and Y both pointing to this memory, which has mostly been initialized. Finally, we perform the string copy on Y. and we copy the data from the end user. We copy the parameter into the buffer that's in the memory. And now we can have some data in there that's attacker controlled. If at any point we now assume that X still contains the trusted data, we will be sorely disappointed, because X has been overwritten by the attacker and can no longer be relied on to be correct. This is one of the ways in which a use after free vulnerability can be exploited. So how is this attack useful for the attacker? Well, we've seen one example, but there are many ways in which you could use a use after free vulnerability, and they are widely exploited. For example, the Linux kernel is known to be relatively vulnerable to it, because most of the other vulnerabilities have been fairly successfully found. However, for use after free vulnerabilities, static analysis is not very effective, because it's very dynamic. You need to really be able to reason about the lifetime of the pointers, which is very hard without executing the program. So, what can we do with this attack? Well, we can typically bypass some length restrictions for buffer overflows later on. So if we overwrite some data, even if it's inside the bounds of the buffer, any index or size that we overwrite might trigger a later buffer overflow. Another approach is to override some fields that should not be attacker controlled. So let's say that in one of the objects, the original object, we had an integer, which was attacker controlled. And in the other object, we have a pointer. Obviously, the attacker should never be able to specify a pointer. So if these overlap, and the attacker is able to write to the integer at the same time that there's also a pointer stored there, then they will be able to typically perform some attack. For example, this might be a good basis for an arbitrary read or arbitrary write primitive. Now, if we override some validated data with incorrect data that will not be validated, we also have this issue. So let's say that there's a path in the program and the path is overwritten by something else using the use after free. Then we are able to bypass authorization. Finally, even if we cannot corrupt any data, use after free is also a good basis to leak data. So if we can print, using the dangling pointer, some of the data, then we might be able to print what is stored into the new buffer. Now, if the new buffer contains sensitive information, this might be a very sensitive vulnerability in itself, even if nothing is being corrupted. Now that we've discussed use after free vulnerabilities, let's look at the other major class of temporal vulnerabilities. So whereas a use after free vulnerability means that we're using a buffer after its intended lifetime, uninitialized variables mean quite the opposite. So in the case of an uninitialized variable, what happens is that we read a buffer before it has been initialized. Now, it's important to know that in C, and also in C++ to some extent, local variables and malloc buffers are not automatically initialized to 0, or anything else for that matter. Only if we explicitly initialize them is a value stored in there. So if we do not initialize them, what is the data that is there? Because there has to be some data. So this is simply whatever was stored in the same location before. So this means that if you have something on the stack, it's going to have some prior local variable, return address, frame pointer, or something. If you have something on the heap, it could be anything pretty much that was stored on the heap previously. So if we use this data, it is, from the programmer's perspective at least, undefined what will happen. We don't know what information is stored there, and it is a bug to use this data. Now in practice, it is very common that this data is simply 0 if it hasn't been used yet. But if the memory has been reused, whether on the stack or on the heap, then something will probably be there. And this data will be used instead of the zeros that perhaps the programmer was expecting. So this vulnerability can, to some extent, be found using static analysis. Compilers do try this. They try to give you a warning when you use a variable uninitialized. However, they cannot always know this. And compilers typically, for example, ignore cases where you use arrays, struct or union members, or malloc buffers, or essentially anything that goes through a pointer without initializing it. The compiler is simply unable to predict whether there is a risk of the variable being used uninitialized. And also compilers tend to be very conservative in the sense that they do not warn unless they're pretty sure that there's really something wrong. Otherwise, programmers will simply disable the warnings, and it's not useful either. Now let's say that there is an uninitialized variable vulnerability in a program that we want to exploit. Let's give some idea of how we could abuse the situation. So we assume we can craft some input that forces a variable to be initialized to a value that the programmer did not anticipate. This is our high-level approach. So first the programmer allocates the buffer or variable x, which is normal. X then uses the buffer to store something under attacker control. Again, this might be completely benign because it's common to store user-specified data. Nothing wrong here, still. So the buffer is now freed, just like we saw in the use after free case. But now we allocate another buffer overlapping with it, the buffer y. Now this is where it diverges from the use after free case. So in this case, the program does not initialize y or some part of y, which means that whatever data the attacker put in x remains there. Now x was attacker controlled, but y might not be supposed to be attacker controlled, or there might be restrictions to what a potential user could put there. So the data still remains there, and the programmer probably did not anticipate this data to be user controlled. So the program uses y without initializing it and gets an incorrect result. So just like in the use after free case, it's very common for this type of vulnerability not to show up. So in the normal case, where the attacker didn't deliberately cause x to be allocated in this spot, it might very well be that y happens to contain null bytes. And in this case, it's typically harmless. So we do not see the uninitialized read until an attacker actually abuses it by putting some data in the location where the buffer is going to be. This program shows a very simple example of an uninitialized variable on the stack. Now we can think of many other scenarios, but this is a relatively simple one to demonstrate how you could abuse this. So on the left we have the main function, which calls the show function twice. Show takes a string and then allocates a local buffer on the stack to store this string. It concatenates a new line and then prints it to standard out. So, where is the vulnerability here? Take a moment to look. It's not that obvious actually. So, if you haven't found it yet, pause the recording and go find that vulnerability. Where is it? It's actually here. Stringcat performs concatenation of strings. So it looks for the string that's already there, searching the null terminator, and then appends the source string at the end of the destination string. Now, the first call, nothing is stored in the buffer yet. So the buffer is initialized to 0. In effect, stringcat operates exactly the same as string copy at this point. However, the second time we call the function, some data is actually there. At this point, stringcat will find the data and append the other data at the end. Right? So this is not a completely obvious vulnerability. But the issue here is really that stringcat is performing an uninitialized read. We put nothing in the buffer yet. Had we used string copy, there would be no issue, because string copy doesn't read the buffer, and it's fine to pass an uninitialized destination buffer to string copy. So, what is going to happen? Let's start execution. At first, we only have a return address and RBP for the main function. Then we call show. Well, again, we add a return address and RBP. There are, at this point yet, no local variables, but we will allocate one now. So, the function allocates the buffer line using alloc a, which means we add a local variable line here, and also the buffer. So as before, the convention here is that the dark parts are actually initialized, whereas the lighter parts are not. So only the literal string specified by the program is now loaded into the buffer. So it's loaded into the start, the other parts remain uninitialized. In practice, because the memory has never been used before, it's likely to be 0. So now we get to the return of the show function. Now at this point, it deallocates the part of the stack that was used for the stack frame of the show function. Right? So the deallocated parts are now marked in red stripes. The data is still there, but it's just no longer supposed to be used. So now the second call. We pass an attacker supplied buffer and we allocate enough data to store this buffer. Right? We have the string length +2, which should be enough space to add the new line as well as the null terminator. The second call of the show function brings us back to the point where everything that is shown here is officially allocated. However, now there's already a value in there, your input \n, and a null terminator. So this string remained in the memory, is now allocated again, and we cannot distinguish it from the empty buffer that should have been there. So string cat will see this data and add the attacker control data at the end, which means that we're writing more data now than expected. So in principle, we allocated enough data on the stack to fit the string provided by the attacker. But the extra characters that are now already stored in the buffer, which we are concatenating to, allows us to overwrite past the end of the buffer. In this case, it allows us to overwrite the line variable, which doesn't matter too much, as long as we make sure it retains the correct value. And then we can overwrite the frame pointer and the return address. So let's point the return address to the shellcode, and then we have a correct memory corruption attack, and we can hijack control. So this example showed that you can in principle use uninitialized reads for memory corruption attacks. However, the more common scenario, perhaps a little bit less impressive, is information leaks. So uninitialized variables are a very common source of information leaks. So be sure to initialize your variables and be sure to explicitly wipe sensitive data after its use. So passwords, encryption keys, personal data, and so on. If this data remains in memory and is read uninitialized, it might somehow end up with the attacker, which we really do not want. Of course, and this is much harder to prevent, there's also the risk that you might leak an old pointer. For example, if you leak something from the stack, it's typically full of pointers. And as before, just leaking one pointer might completely compromise the ASLR defense. So this is also an important risk for uninitialized variable vulnerability.